To help get a better handle on the ideas of potential and kinetic energy and energy conservation, we're going to consider an ideal spring. Okay? For an ideal spring, the conservative force exerted on whatever mass is attached to the spring, whatever object is attached to the spring, is negative kx. Just a very simple linear restoring force. And you should be familiar with this. This has been done in the stuff you're working on right now. So the change in potential energy as we go from point x1 to point x2 then is equal and opposite to the work done by the conservative force from x1 to x2. The work done by the conservative force is just the integral from x1 to x2 of the conservative force with respect to x, and the potential energy change is the negative of that. Now, of course, these negatives go together to give you a positive. Your antiderivative is 1/2 kx squared. Evaluated between x1 and x2, the change in the antiderivative, in other words, from x1 to x2, is just 1/2 kx squared to x2 squared minus 1/2 kx1 squared. Very straightforward integration. We've already seen that much earlier in the course, or at least fair time ago. Okay. Now, if your reference point is x equals 0, now you can take any point as your reference point, but if your reference point is x equals 0, the point at which the spring force is 0, or the net force in your oscillator is 0, then the potential energy is going to be just the negative of the integral from 0 to x of negative kx dx, or just 1/2 kx squared. Now again, reference point 0 means we're measuring potential energy changes from the x equals 0 position, and whatever the potential energy change is from the x equals 0 position to the position at which we want to find the potential energy is equal to what we call the potential energy function. So potential energy is now a function of x. We're not just talking about change in potential energy, we're talking about potential energy as a function of x, and that's 1/2 kx squared. Again, relative to this 0 position for the potential energy. Okay, so the maximum value, okay, let's assume now that x has some maximum value. In other words, we get this spring in motion and it oscillates with whatever mass or object we have attached to it. And it oscillates with no friction, no resistance. The spring itself has negligible mass. So we just have an oscillation that continues forever with no loss of energy. In other words, non-conservative forces exert no, non-conservative forces are negligible or non-existent. So let's put that up here. No non-conservative forces. Okay. In that case, there's going to be some maximum distance on both sides of equilibrium, and it's going to be equal on both sides. Some maximum distance that the oscillator will move on both sides of the equilibrium position. So that we have for that oscillation a maximum potential energy of 1/2 Ka squared. Okay? Now this is for some oscillation. We have a maximum position, and that's called the amplitude. And the distance from the equilibrium to the maximum position is the amplitude. And that could be plus or minus A. X max would be a plus A, minus A would be a maximum in the negative direction, but I'm not going to split hairs on that right now. Okay, your maximum potential energy would then be 1/2 Ka squared. So what we have potential energy versus X. Okay, out here at A, we have our maximum potential energy, and at negative A, we have the same. So that's 1/2 Ka squared. Now the potential energy function is 1/2 kx squared. That's nothing but a quadratic function with a vertex, with a graph whose vertex is at x equals 0. So we simply have a parabolic function here. Not a particularly symmetric parabola, but you hopefully get the idea. Okay? And right here is our potential energy function. And I'll call that PE of x function. Now, up here we have the 1/2 Ka squared, which is the potential energy at these 2 points. We have a line here where the potential energy is equal to 1/2 Ka squared, and that equals the total energy of the oscillator. Because there are no non-conservative forces, if A is the position at which the oscillator stops, its kinetic energy is 0. Total energy is the sum of the potential and kinetic. And that should actually be total mechanical energy, just to be complete. Total mechanical energy of any system or object is the sum of its potential and kinetic energies. And that maximum energy is achieved in the form of potential energy at the extreme points of the oscillation. Now, at any point in between, you have less potential energy than you do at the extreme points, so that at any point here, say this is a point here, at point X, you have the potential energy which I could denote PE of X, and you have the difference between the potential and the total energy. Now, what's the difference between the potential and the total energy? Well, the total energy is potential plus kinetic. The difference between the potential and the total is therefore the kinetic. So not sure why I changed colors of chalk there. Yeah, it doesn't matter. Okay. I think I now know, but so that the kinetic energy would be represented by this arrow. Now, you could do that at any point. You could draw a curve and actually be kind of pretty, so maybe I'll draw it. So without all the labeling, you have a parabola here. You have a total energy here. And at a sequence of points, you can indicate the potential energy by a series of arrows. Potential energy increasing as you move away from the equilibrium point at the center. And you have the corresponding kinetic energies. So kinetic energy in yellow, potential energy in orange. We can do a similar diagram for the situation where you have a car and magnets. Now, here we don't have an oscillatory system, although we could modify the car and magnet system to be oscillatory. You have car and magnets relative to infinity. So I've just drawn this curve relative to infinity, and the curve is actually quite a bit sharper. It comes up very steeply and then levels off fairly quickly. But just to give us a schematic, let's say that this is the position, the x coordinate, at the closest approach, so that we can project up here so we get the potential energy at closest approach. Now we're going to take that as the maximum potential energy of our system because we're not getting any closer, and potential energy only increases if we get closer. We're going to assume an ideal case, I'll say there's no WNC, no work done by non-conservative forces. No non-conservative forces present. Okay? In that case, if there are no non-conservative forces present, well, remember that change in kinetic plus change in potential energy equals the work done by non-conservative forces, and we've implicitly applied this up here. Any loss of potential energy is going to be accompanied by an equal and opposite, an equal gain of kinetic energy, and vice versa. Okay, so potential and kinetic energy are in this balancing act. Their total is always the same, as is the case in these diagrams, and that's also going to be the case here. That's going to be the case anywhere where there are no non-conservative forces. So I'm going to draw a line across here. This is your maximum potential energy equals total energy. So what's going to happen? Well, your potential energy is constantly decreasing as we move away from this point. But the sum of kinetic and potential has to be always the same because the work done by the non-conservative force is zero, so that your kinetic energy, and I'm drawing those arrows in the wrong direction, is this. Okay? So here's your kinetic energy. Here's your potential energy. What does this tell us? This tells us that as the car moves away from its point of closest approach, in a situation where there are non-conservative forces, like me holding it back, or like friction, that the potential energy decreases, the kinetic energy has corresponding increase, so the car speeds up. Now that might come as a surprise to you, but that is what happens. The car does speed up. You could test that, and of course you have, and you know how that works.